Okay. So I've been too obsessed with watching election stuff. So, and all of a sudden, like, class. Shit. So, and after class is over, I'm sure I'll just resume my obsession. So, and who knows, maybe some of you will too. Okay, so one thing I want to discuss is how we're going to wind things up with all the homework that there is, because right now what I have posted in Canvas is 9 homework assignments, everything up to this week's section 9.3, and then I have in mind one more. Actually, I think I might have already. I thought I'd already put it out there. Let me check. No, I've not. Or I don't recall if I've picked out the problems yet. Nope, I've not. Okay, so silly me. Anyway, there's supposed to be one more for next week's section, which is 9.7. So a grand total of 10. But I also know that those of you who are furthest along with the homework are only on, I believe, homework 6. From 8.2. Yeah, homework 6. So, and the thing is, we're running out of semester. I mean, 1 month from now is the end of finals, and plus the fact that you have your other classes to deal with. You have your respective real analysis hell, and and possibly over classes too. So I don't want to have a situation where it gets down to the end of the semester and then all of you have this ginormous backlog, like dealing with after Thanksgiving break, and then are having to deal with like a few assignments at once. Well, I was dealing with our finals. 3 of you are teaching, so you're dealing with those finals also, grades, blah blah blah. So it is something I'm concerned about, because I want to allow enough time, and that's why I've let deadlines kind of slide. And even though like each new deadline is a week after the previous one, of course I'm not really not actually enforcing them. And things kind of fell behind right away just because the first assignment was that MATLAB one, which was quite an ordeal for everybody. So I've been pondering today, like, okay, what should I do? So as an attempt to just lighten the load a little bit, I'm going to first say that your lowest assignment I'll just exclude. So if it gets down to the end and there's just too much, then you can just go ahead and kick one assignment, essentially. And then the other thing I want to throw in there is, last class when you had been asking questions about the problems in 8.2, and I mean, when I create these assignments, I just go through all the prompts in the section, and I feel like, okay, this is a good one. Oh, this one's not workable, et cetera, and I just sort of curate what I have here. And sometimes that curating process breaks down. And what happened in this case, when you had called my attention to one of the problems, 8 to 10, I looked at that. It's like, wow, why did I pick that one? Like, there's a lot more involved in that I was thinking about at the time I was going through all the list and throwing some problems in there. And plus the fact that I'd thought quite a bit about 12 and 13. It's like, do I want to include those? I went back and forth on that one, and I thought, okay, I feel like it'll be safe to include them as long as I throw in some hints. So, so because A210 is quite a production, compared to other problems, I'm going to sweeten the deal a little bit. So as it is, you can drop one assignment. If you decide to go through with 8.2.10, I'll let you kick a second assignment. And so I feel like that might kind of be an even trade there. I mean, at least a couple of you are in the midst of homework 6 right now. I'm not aware of anyone who's actually jumped into that problem yet. Because you've been working on the other ones, or working on earlier things. So if you, so assuming that you haven't gotten to that yet, you can just go ahead and, in your mind, delete that from homework 6. And if you want to do it anyway, in exchange for not having to do some other assignment, go for it. What I would recommend, if you do decide to go through with it, and actually I'm going to start a screen share here. Or try to. Where'd it go? Okay. Okay. Let's see. One of the other problems that was assigned in this was this one, orth poly. That's kind of like make Lagrange, where you're building up a bunch of orthogonal polynomials. A good way to handle A210, which is best two-norm approximation, or best two-norm approximation, is this function needs to also generate orthogonal polynomials. It's just that they're more general, like if they involve a weight function, therefore the integrals have to be computed numerically and so forth. So if you want to go ahead and do this one, what I would suggest is you take this function and generalize it to work with an arbitrary weight. So the W that's passed to best two-norm approximation gets passed down to a modification of this function, so that it'll generate orthogonal polynomials with any weight. And whereas in problem 825, you could use MATLAB's polynomial functions to evaluate whatever integrals you have. If there's a weight function handle coming in, you can't do that anymore. You'd be using integral instead. So that way, so it's a good way to break down the rather large task that we have here. So basically, what do you need to do? You need to generate your orthogonal polynomials. So you're delegating that to this modified version of orth poly. Once you have them, then you would be using a formula like, where'd it go? Oh, a formula like this to actually compute the best two-norm approximation. Because you'd be taking inner products of your orthogonal polynomials with your function f, and then multiplying those by your orthogonal polynomials to construct your best approximation. But these kind of inner products, you're also having to do when you're generating the orthogonal polynomials. So once you figure out in one place, you can do the same thing in the other. So, okay, I'm going to switch to my notes. Okay, so I need to unshare and reshare. So I want to have this in writing. Ah, dang it. Okay. Actually, I think what I'll do here. All right. I have a notes in here from Monday's class, but really this is not about that. Okay, so there's a nice formal name for today's topic. Okay. Okay, so not dropped. Okay. Okay, so just so you have clarity on that. Okay, now whoops. Okay, so to summarize what I was talking about. All right, so you're going to modify this function to accept function handle for a weight function w. And then in that modified version, you got to use integral to compute all inner products, just because you're not dealing with just polynomials anymore. That function orth_poly is designed to generate monic orthogonal polynomials. So unless you change it yourself, and there's really no need to. So whatever polynomials you get from your modified orth_poly function, will, unless you make a change to it, are monic. So meaning leading coefficient 1. Therefore, they will not be orthonormal. And this is something that, in retrospect, I wish I had spelled out more clearly in the book. So your best two-norm approximation has this form. So fn of x 0 to n of cj pj of x, where the pj are the monic orthogonal polynomials. So I'll label those as p0, p1, etc. And the coefficients, and you see this formula before, but again, I want to have things spelled out clearly here. So you have the inner product of each polynomial with f as a numerator, and then inner product of each orthogonal polynomial with itself in the denominator. Okay. So this function will generate your orthogonal polynomials, storing your coefficients in a matrix. So then you can use those for these inner products here and here. And what you're doing is Fn, so in your code, each polynomial Pj and Fn that's a MATLAB polynomial, a row vector of polynomial coefficients, like usual. So you would be multiplying each one by the appropriate coefficient and adding them up. And coefficients computed using these formulas. Okay. So framework, if you want to go ahead and do this problem, which will still be a pain in the butt. Okay. I want to check something here. All right, so I've been 4, 5, 12, 10, 4, 7, 12, 13. Okay. Question. I know that at some point, if it's probably on Monday, I had talked about problem 825. Has anyone actually started trying to do it yet, or have you not gotten around to it yet? Okay, that's a no. Okay. Speak now or forever hold your peace. Or unmute or forever hold your peace. Okay. All right. All right, I'm gonna do it like this. I'm gonna throw 825 in here. So I guess so equivalently, all right, so homework 6 now consists of just these problems. Okay, 8.2, 4, 7, 12, 13. We also have, and I'll call this homework 6 prime. Actually, no. I'll call it 6A. 8.2.5 and 10. So it's like I've broken those off into another assignment. So with that in mind, now there are 11 homeworks for because one of them has undergone mitosis. But you can drop any 2 of them. Okay, so questions about this arrangement?
I have a question.
Yeah.
So, first of all, thank you.
Okay.
It's very helpful. But also, so I know you're calling. So are we actually, I know you're writing 11 assignments, but this alternate homework, like, since we can make maybe this decision later if we go through and do these extra problems versus another homework, are we submitting this as an alternate assignment, or would you want us to submit it back into homework set? Like, is it going to be great? Like, is it still 10 assignments for real and we're being aided on grade on 8, or is it now we're just calling this a complete separate assignment and we're being graded 9 out of 11?
Look this way, because what I had in mind was, if you don't bother with these other 5 and 10, you would drop 1.
Right.
But that's equivalent to having it as one of the assignments. Therefore, you always drop 2.
Right.
Yeah. So I thought I'd like streamline my deal that way. So, yeah. So I went up to 11 assignments to tell you have 9. So, and I think what I'll do to simplify bookkeeping is I think I'll make a change in Canvas, where I actually will put this in as a separate thing. And then like I'll edit the homework 6 that's in there now to remove those 2. And break them off into the other one. Yeah, because I think just from a grading standpoint, it'll work nicer that way. Because then I can just tell Canvas, drop 2.
Yeah. Thank you.
All right. Well, I hope that'll work. Because I mean, you all have a lot to deal with. Well, I know at least some, if not all of you, had more to deal with lately than you bargained for. And I never want anything y'all doing with me, whether it's like this class or whatever class is coming up next semester, or for some of you research. I never want one of those things to be the straw that breaks the camel's back. So we'll just see how this goes. And as we get down to the end, especially when it gets into finals week, like final grades are due. Actually, I'm going to make a note of this also. Okay. I have to turn in. Whoops. Those are due on Monday, December 7th at 11 a.m. is a traditional time. As far as I know, it hasn't changed. It's always been like the Monday after finals week, 11 a.m. One semester they made it 8 a.m. I'm not sure why. And then they changed it right back. So I guess they were experimenting and it failed. So what that means is, what I would like is, whatever you got going, everything submitted by the preceding Friday the 4th. Because that way, since I'm doing your class and 102 and 326, that I have enough time to sort out everything for every class. I mean, you guys are a small class. I can show a little leeway, but this is what we're going for. Just to say, here's where this comes to an end. So, but I mean, as it gets into finals week, I'm gonna, especially since there are only 4 of you, I'll be checking on you individually just to see where things are at. So, okay, so hopefully that will impose a reasonable upper bound on your stress. Because the math may be challenging. Sometimes it seems like, all things considered, the math ends up being relatively easy part compared to some of the other crap that goes on. Like y'all dealing with your own students and so forth. Okay, so that's what I wanted to put out there about that. Okay. So any questions about anything that I've written here? Okay. Now, one thing that came up when I was helping one of you, I thought it would be a good idea to share with all of you. Just describe it a little more clearly than I have to this point. Why is it that this how orthogonality is so helpful? Okay. Whoops. Okay. No, seriously, orthogonality is one of my favorite concepts of all of mathematics, just because I personally benefit from it so much, and a lot of other mathematicians do too. So for least squares problem of finding the best approximation such that this norm of the error is minimized, where these polynomials, the phi's here, okay. Wait, I need to write this a little differently. So each phi j is a polynomial of degree j. Now, one very important consequence of each polynomial being of a different degree it ensures that the polynomials are linearly independent. And because they're linearly independent, these coefficients are unique. Okay, I need to close this run-on sentence here. So right now, I'm not doing anything with orthogonality. I'm not even assuming that these polynomials are orthogonal, just that they're different degree. So the equations that must be solved and what I'm going to do at this point is actually okay. I need to go back to my old notes. Okay. Sorry, I'm looking up a bunch of things at once here. Okay. All right. First, what I need to reproduce this exactly as I had it in the book, because what I have in the notes in the book, they are equivalent, but they're expressed using different notation. So I want to reconcile that. Okay, so in trying to solve this problem, these are normal equations as described in the book. And how I wrote them in the notes, back from October 12th, I can write them this way. Okay, where we have the inner product, the standard inner product on AB, and we're assuming that F and G are real. Oh, what happened? Dang it. Okay. I hate when stuff decides to go into another page all of a sudden for no legitimate reason. Okay. So this allows me to just express the system of equations in a more concise form. And I need to emphasize that this is true for every k going from 0 to n. Okay, so book, notes, but they're saying the same thing. Here I don't have a weight function, although one could describe a weighted least squares problem, which there would be a weight function in here, but we won't get into that now. Okay, so what we have here is a system of a form. Calls n, c is equal to f, where the ij entry of a matrix n, so this is an n plus 1 by n plus 1 matrix. So each entry is an inner product of two of these polynomials. The vector c is just a vector of all of these coefficients, VC's, that we're looking for. And each element of a right-hand side vector f is an inner product of one of these V's with f. So in general, to solve a least squares problem, once you've picked out what these polynomials would be, like for example, they could be the monomial basis, like 1, x, x squared, etc. Then you have this system of equations, and you're solving this system by Gaussian elimination or in MATLAB using their backslash operator. Now, so solving a system requires order n cubed operations generally. It's similar to if you're finding a polynomial interpolant using the very first approach I showed you, where you set up a system of equations like this involving a van der Waals matrix, and that too requires on the order of n cubed operations for a degree n polynomial approximation. And we prefer not to do that. So what we have here, by contrast, okay, so if these polynomials are orthogonal, then the matrix reduces inconsiderably okay. Need to fill in the rest of this. All right, so so this is a matrix. This is a diagonal matrix. It should have more zeros in this. Okay. It puts in these backslashes that cause space, and I'm not sure why it does that. Okay. So this is a diagonal matrix. So we only have these entries on the main diagonal, and all others are 0. And that's where we get this formula that you've seen. Because we have these n equations and n unknowns, and because it's a diagonal matrix, we can just solve each one independently just by dividing each entry of a right-hand side by the corresponding diagonal entry. So once you have these inner products computed, then there's only order n operations after that. It really is just performing n divisions, and that's the key advancement here. Just to greatly simplify this task of obtaining the best two-normal approximation, instead of having to solve this whole system. So if they're, they are orthonormal, well, all that means is that inner product of each one of itself is equal to 1. Then there's no system to solve at all. It's just the inner products. So I just wanted to make sure that I painted this contrast of trying to solve the least squares problem with or without orthogonal polynomials. what the distinctions are between not having orthogonal at all, just linearly independent, then orthogonal, and then orthonormal from a linear algebra point of view. So equivalently, in this case of orthonormal, the matrix N is just the identity matrix. So no system to solve at all. It's already done. Okay, so questions about any of that? I missed, dang it. Okay. There's one other thing related to orthogonal polynomials that I want to show you. And this is actually going to set the stage for the last topic of a semester, like from section 9.7 that I'll get into next week. Okay. And this is something that will help you see like how orthogonality can be applied to obtain various things. So basically how you take advantage of the fact that certain functions are orthogonal. Okay. Now, I made a comment when covering orthogonal polynomials about the roots, and I think at that time I was in a bit of a rush. Okay. So if you have these polynomials, so phi 0, phi 1, etc., are orthogonal with respect to this inner product, with some weight function, then the roots of each polynomial phi j, at least for j greater than or equal to 1, because phi 0 is a constant, therefore it doesn't have any roots, these roots are real, they are distinct, and within the interval AB, which is quite unusual because normally when you have any old polynomials, even if the polynomials have real coefficients, the roots can be complex, the roots can repeat, and who knows where the roots might be. So the fact that we know all this about the roots just because of orthogonality is a bit striking. And I had seen in another textbook, like the one that used to be used for Math 772, a proof of this, and I thought that was all well and good. But for the book, it's like, you know what? I don't want to just include that proof. Even though I could always, include it and cite it properly. What I'd rather do, if I could, was come up with a different way of proving it, and that's what I want to show you now. So what I'm going to do is show you how orthogonality can be used to show each of these three things one at a time. So first I'll show they're real, then show they're distinct, then show that they're in AB. And This is a good exercise in proof by contradiction. I'm going to assume that each one of these things is false, and so I get a contradiction. So maybe this will help you thinking about these things in real analysis, for instance, or wherever else proofs are done. Okay. Okay. So what if the roots are not real? Now, in the case of j equal to 1, we have a linear function. Well, it cannot happen when j is equal to 1 because now the thing I want to keep in mind is actually before I should say this before I jump into these cases. All of the coefficients are real. Why? How do we know this? Because the coefficients come from a three-term recurrence relation. I have those formulas for these coefficients, these alphas and betas, that you also see in the text. And since those are inner products of real functions, they themselves are real. So we have real coefficients. All right, and that's why in the case of j equal 1, that's a linear function of real coefficients. It's going to have one easy to obtain x-intercept that's going to be real. So for a linear case, it's a non-issue. Okay. All right. So what about j greater than 1? So what we do in that case is going with our assumption that the roots are not all real. Assume complex roots. C plus or minus di. Because if you have a polynomial with real coefficients, any complex roots that you do have must occur in complex conjugate pairs. So that gives me some information about the factorization of phi j. So that'd be equal to phi j of x equal to x minus c plus di times x minus c minus di times some other polynomial that's of degree j minus 2, because I'm taking 2 powers of x out from here. So then what I can do is I can FOIL this out. And what it'll give me is, okay. All right, so I'm going to have x squared. Okay, so then I have minus cx minus dix. Then I have plus c squared. And then I have, okay, so I did all of that. And then I have minus cx again, so that's 2cx. And then I have plus cdi. Okay, and then I have here I have okay, so plus dix, and then I have minus CDI, and then I have plus DI and minus DI, but that's going to be plus D squared. And now there's a lot of cancellation. All of the imaginary terms cancel out, so this whole thing is real. Okay, and here we have a perfect square, so that's x minus c quantity squared. Oh, whoops. Okay, so phi j now has this factorization. So now what I can do is, if I look at this integral, of x minus c squared plus d squared, and then q j minus 2 of x squared. All right. Now, this integral, we have a non-negative function here that's also not zero everywhere, and here too a non-negative function. So this whole integrand is non-negative, and it's going to be positive at least some points. Therefore, you know what? Actually, it doesn't follow from a previous statement, so I shouldn't say therefore. I'm sorry, what?
Why is the q squared?
Oh, you'll see. Yes, this is a bit contrived right now, but so because what I can do is I can take this integral and what I can do is take one of these qj minus 2s and lump it in with this factor here. So I'm going to put brackets around that whole thing. Okay. But what is this whole thing? That is exactly phi j. Now, a slightly better answer to your question, Chelsea, about as to why I squared it. I wanted to make sure that I needed to have an integrand that was a perfect square to ensure that the integral was positive. Okay. But now I can write it this way. I have to write it this way because I ran out of room. This integral is an inner product of phi j and qj minus 2. Is that a big deal? Because phi j is orthogonal to all polynomials of lesser degree. Look what we have here. Phi j is a polynomial of degree j. I factor out a quadratic. What's left is still a polynomial, but of lower degree. So for that reason, this It therefore must be equal to 0. But I've just also said that this integral must be positive. This inner product or integral, however you want to look at it, is positive. So I've shown that it's positive and 0 all at the same time. And that's a contradiction. So therefore, the roots must be all real. Questions about that? All right. And this is how a lot of things are proven in using orthogonal polynomials, that you find a way to express something as an inner product of an orthogonal polynomial with something of lower degree, because then you can immediately conclude as 0. And hopefully that's useful for whatever it is you're trying to prove. In this case, getting a contradiction. Now, there's still the other cases showing the roots are also distinct and they fall within AB. And those two items I can prove using an approach similar to this. What if we assume roots are not distinct? So we have some root that I'll call C that is at least a double root. So it has a multiplicity greater than or equal to 2. So now I can have a similar factorization of phi j. I can write as x minus c squared times some polynomial of degree 2 less, because phi j is I factored out quadratic. What's left is of degree j minus 2. Oh, and actually, I should be more precise here. All right, that it has that degree, thus the subscript. Okay. So now we have this. Now if I take this integral, that's similar to the last one of x minus c squared qj minus 2 of x, and here I also square it. But that is, here we have equal of a non-negative integrand, which therefore is positive, but that's also equal to the inner product of, if I take x minus c squared with one of these qj minus 2, that is phi j, with qj minus 2. Same kind of situation. An inner product of an orthogonal polynomial with some polynomial of lesser degree, which therefore must be 0. So again, I have the situation of something is positive and 0. Which is also a contradiction. Questions about this one? Friends, like, your rooms are so dark all of a sudden. Okay, sorry, just stuck out to me. All right, last item. What if the roots are not within AB? Okay, so we know the roots are real already and distinct. So let's suppose we have a root that is outside the interval AB. So now what I have is I factor it out, and now what's left over is a polynomial degree j minus 1, because I've only pulled out a linear factor. And we have, if I have x minus c times 1 of x squared, so very similar, I can actually claim that this integral, I can't say it's positive using the same reasoning that I did here, because I do not have, this is not a perfect square, or it's not a sum of perfect squares like in the first part. What I can say though is, basis factorization and the assumption that this root is not in AB, I can say that this integral is at least non-zero. Can anyone tell me why? I can't say that this integrand is positive or even non-negative on AB, but what can I say? Yeah, this is a pretty hard one, actually. But I wanted to put it out there. All right. It's non-zero because the integrand does not change sign on AB. Now, you can see why this part will not change sign, because it's a square. What about this part? Here we have a linear function. It most certainly does change sign. But where? At what x value does this linear factor change sign?
After the root C?
Yes. Yeah, because that is the only point at which this linear factor will be equal to 0, and since it's a line, it will represent a sign change. Okay, fine. There's a sign change outside AB. So in AB, this integrand does not change sign, only outside of AB. So whenever you have an integrand that does not change sign, unless it's 0 everywhere in AB, the integral is going to be non-zero. In other words, the integrand is either always non-negative or always non-positive. Okay. However, just like in the previous parts, this integral is the same as the inner product of phi j. If I take x minus c with one of these qj's, then we have an inner product again of phi j with a polynomial of lesser degree. And therefore must be 0, contradicting this finding that it's so. Therefore, this assumption about the root not being in AB must be false. So the roots are real, distinct, and they lie in AB. You had to prove this already for the Chebyshev polynomials, but you approached it a very different way because you had an explicit formula for the Chebyshev polynomials, and you could handle it that way. Because the Chebyshev polynomials are a family of orthogonal polynomials with respect to a particular weight function, so they would have to follow this too. So because of these root properties, it therefore makes sense to use the roots as nodes of a quadrature rule. Because with quadrature rules, I'm approximating an integral by a sum, like f of xi times a weight, and those valuation points, those xi's, the nodes, they ought to be in AB because we're integrating over AB. All right. So that will be next week's topic. What are the benefits of using the roots of an orthogonal polynomial up a quadrature rule? So that some very nice things happen as a result of doing that, all a consequence of orthogonality. So that's what I'm trying to get across here. Orthogonality is a wonderful thing because look at all the things that you can prove with it, and these really unexpected properties that orthogonal polynomials have. So these kind of manipulations involving these inner products is something I wanted to expose you to, so you can see how orthogonality is used in proofs, and just because it's cool, but or I think so anyway. Okay, so in the last few minutes that we have, does anyone have questions about, well, anything? Well, okay then. Just making sure. Okay, well, so I'm going to probably hear from you individually anyway about one thing or another, so we always have that. Okay, well, I guess I'll wrap up before the darkness follows you all whole. But yeah, I want to hopefully, this is a sufficient, relief for the homework so that, you can get it all done and not be pulling your hair out because you're much too young for that. Okay, so we'll just see how things go. So, all right, let's see. What did you post? Okay, so I just have these notes to post. And I'll go ahead and change the assignments in Canvas like I described. So. And thank God the day is over. Well, okay, for me anyway. Sorry, Chelsea. Okay, stopping the recording now.